Well, good afternoon. My name is Brian Zelli, and I'm speaking from MITRE Engenuity here in McLean, Virginia. Thank you for joining us today for this afternoon's Open Generation Government Liaison Roundtable with NASA's Langley Research Center in Virginia, featuring Mr. Andy Lacher, the Chief Technologist for Future Airspace Operations. NASA likes to say sometimes that the first A in NASA stands for Aeronautics, and the administration has focused on leading-edge research of things that fly since its inception. UAS operations are a key part of the future of aeronautics, and today Andy will be sharing research that's underway for UAS and communications. This will be an interactive roundtable, so please feel free to ask questions during the presentation via the chat, and then later we'll be able to speak as well. After the presentation, we're going to open up the floor for an interactive discussion. I ask you to please keep your microphones muted unless speaking, and please note that this roundtable will be recorded. And Marisa, if you have not begun recording, please do so at this time. And Andy has several colleagues with him today from NASA, Jennifer Kibler, Tommy Jordan, Sam McGill, and I hear that Danette will not be joining us, and you'll hear more about them later on from Andy as well. So unless there are any other announcements from our side, I'd like to hand over the microphone to Andy.
Thanks, Brian. I'm sharing my screen, and hopefully you can see the screen share. Is that correct?
Yes, we can see you just fine.
Good. Okay, I'm going to share a little bit about what NASA Langley is doing in the area of not only unmanned aircraft, but also advanced air mobility. And I'll talk a little bit about what those things are and how it might relate to 5G and some opportunities to potentially collaborate. I'm a confident speaker, but I don't mind being interrupted with questions. In fact, if you're asking me questions about things I said, that means you're listening to what I'm saying. So feel free to interrupt me if you do have a question. I might not see a hand raised virtually using the Teams feature. So just jump in, put your mic hot. There's not that many people, and we can jump in that way. And for some reason, oh, there we go. So this is the Langley team that's here. Actually, Danette Allen is here. All five of us are here. Danette just doesn't have a microphone, so she can't speak. She can only send in information in the chat, but she's listening actively. And these are the different roles that we all have at NASA Langley. We are mostly focused on aeronautics among the five of us here, but Langley itself does a lot more than just aeronautics. Langley, which is actually existed before NASA even existed, was doing aeronautics research and space exploration research, and NASA Langley continues to do aeronautics and space exploration research, as well as science and some other technology exploration activities. As far as aeronautics goes, NASA Aeronautics is looking at a number of different innovative aspects of aviation. We're looking at fuel-efficient aircraft. We're looking at high-speed commercial flight, the future of airspace operations, as well as things like advanced air mobility, which would include unmanned aircraft. And there's a close relationship between advanced air mobility and some of our future airspace work, because we have to figure out how advanced air mobility will work in a future airspace. And that's really what some of the opportunities we come here to talk about today. So let's talk about advanced air mobility. What is this? From NASA's standpoint, we're looking at really innovative, transformable technologies that enable new kinds of transport, both cargo and people, that is safe, sustainable, affordable, and makes aviation more accessible to a greater number of people and a greater number of missions. This is not unlike the definition that the Senate has adopted in a recent bill about advanced air mobility, but their definition is a little broader, but it includes more or less what we're talking about, which would include small unmanned aircraft delivering parcels, eVTOLs that are being used for urban air mobility, remotely piloted or autonomous regional transport solutions, as well as electric or other propulsive technologies being used in conventional takeoff and landing aircraft. All of that kind of fits under the umbrella of what is being called in the community advanced air mobility. I'll pause and see if there's any comments or questions. So what are some relevant characteristics of advanced air mobility? One, we're going to see increased remote operations. Part of that is due to a lot of these aircraft are not capable of carrying a person on board. They're small, they're lighter. To be able to do missions more efficiently than can be done with current traditional aviation aircraft, they have to be operated remotely, and those are what we often think of as small unmanned aircraft or even medium-sized unmanned aircraft. And we're seeing a pivot toward increasingly remote operations, but we're also seeing an increased reliance on automation for operations. This includes not only remote operations, but increased automation for operations that include the pilot on board. We are moving into a future where people envision that a single individual remotely, rather than operating just one aircraft, a single individual could be remotely operating many flights simultaneously, perhaps a dozen, a couple of dozen, or even more flights at the same time, aided by automation, allowing them to not really be a remote pilot, but really be a remote manager of multiple flights simultaneously. All of that means we are moving toward a very information-centric future for aviation. The FAA actually has a concept where they talk about an information-centric national aerospace system. And their future for both airspace management will embrace information-centric concepts, but recognizing that the flights that are operating in that future airspace will be operating in a very information-centric manner. And all of this means that data, information integrity, and connectivity become increasingly important. And we're here to talk about 5G, and this is where connectivity comes into play. So this future of aviation, this future advanced air mobility concepts really comes down to the importance of data, information integrity, and connectivity to enable this future information-centric aviation operations. So 5G. 5G has a number of characteristics that makes it attractive to advanced air mobility. There's an increased bandwidth, there's potential for low latency of the comm, there's reliability of that communications and packet delivery. There's the ability not only to have device to infrastructure communication, but device-to-device communication. Because there's multiple carriers, there could be redundancy in the network, and the network will be everywhere. And there is the potential for mobile edge computing. That is the ability for some of the processing in a ground system to not have to go back to a centralized location, could actually be distributed to more or less where the antennas are on the ground, enabling faster response times in the future. And there's two really uses of 5G for aviation. One is the actual flight operations themselves, where we would use the 5G connectivity to manage the flights. And that really implies the importance of time-critical communication, with a low latency, where the delivery of information is assured and that the network is available almost all the time. And we're going to see this in controlling of individual flights, the ability for the operator to remain in operational control of the flights, as well as for air traffic management and just general situation awareness. 5G also has a potential on the payload side. And the payload could include sensors on board an aircraft that is fulfilling a ISR type mission, or it could be used by passengers on a air taxi that are using their time in transit productively by remaining in constant communication with the broader network and the internet. And of course, there's numerous applications, far too many to name. And this also puts a greater importance on the bandwidth that might be offered by 5G. I'm going to pause here and see if there's any questions or comments or rocks to be thrown. Okay. And I assume my mic is working.
Yes, we hear you loud and clear.
Yes, thanks.
I just had one question.
Sure, go ahead.
For the air mobility, what is defined from the distance and time? Like, is there any limitations how far you can go and time also?
Well, there's no absolute limitation. When NASA uses the term advanced air mobility, we're thinking local and interregional missions, not necessarily transcontinental missions or not necessarily over the ocean type missions. We're looking at more localized. We don't have a distance set or a flight duration set that is a hard boundary. And if you look at the definition that was adopted by the Congress in legislation that they've passed but hasn't been enacted yet, so I want to stress that it's not enacted by Congress, they have a very similar definition without a precise distance or time defined as what is advanced air mobility. But one can think of it as all the new stuff that is coming down the pipe, with perhaps the exception of supersonic transport.
Okay, thanks.
Can I ask one kind of related question?
Sure.
So I believe like today, right, in flight operations where the air traffic control, they are modernizing and using GPS for I guess air traffic control. So what learnings are we getting from there, and does that kind of help in understanding where we should be going?
Well, certainly there's understanding and learnings that could be gotten from there, and NASA has been doing research in air traffic management for decades now, and so a lot of that knowledge and experience that NASA has over the years is being applied to figuring out how we're going to integrate some of these new operations into the future airspace, because they have limitations on some of their operational capabilities. Not only that, but as you go to increasingly automated flights, and I'll talk a little bit more about this in a minute, there's going to be increased difficulty in following the same operational procedures that we have today. For example, if you have a software that's flying the plane, it's basically, I'm using this term loosely, a robotic aircraft. How is an air traffic controller going to communicate verbally with an aircraft that is being managed by software? That might not be the most effective way to operationally integrate that aircraft into the future airspace. So some procedures will have to be changed, and NASA has that as part of our research portfolio.
All right, thank you.
And maybe one more question. It's Paul Challoner here from Ericsson. So in terms of the objective of NASA here, this is great research work. I love it, love the 5G kind of angle here. But the objective is to research the topic, is to come up with specifications, to regulate, to stimulate the area, to innovate. What's sort of the objective here?
Regulate is definitely not part of NASA's mission. NASA does not have a role in regulating aviation. NASA is more on the innovation, exploring the feasibility and the viability of different technical solutions, and presenting that research to the community. The regulator, which in the United States is the FAA, the operator of the air traffic management system, which in the US is also the FAA, or to the aviation community, including the developers of aircraft. as well as developers of potential solutions that are emerging where you have third parties providing some of the solutions that will enable the operational integration. And I'm assuming many of you have heard of UTM or UAS traffic management, which is a concept where third parties are providing information services that are enabling unmanned aircraft operations. And those third parties are taking some of the technology and some of the learnings from NASA research and implementing them. So let's look a little bit about how communications requirements are actually going to be shaped for the future aviation system. There's a number of different desired functions that we might have for, to enable aviation to operate in the future. And there's a lot of information and services that we might need to provide. And I just listed a couple of examples here under desired functions. And these various functions are going to have implications for the required performance of communication. Doing flight control commands, there's a different amount of latency required for flight control commands that might be required for mission objective changes. So, for example, if I'm directly controlling a flight and I want to change the deflection of a flight control surface, I can't have any latency in that communication. But if I'm changing the route of flight, I might be able to handle a couple of seconds latency in that communication between the ground and the aircraft. Throughput, integrity, and availability are similarly derived from the function you're trying to accomplish. And there are lots of suitable technologies that might be available to meet the required performance. 5G being among them. 5G presents, intuitively a very attractive communications option. And then there are characteristics of that communications option that determines whether it can actually meet that required performance. And a lot of times in the community, we hear a lot of people saying, they go right to the solution and they say, we need protective spectrum in order to operate in the future. Well, protected spectrum might be helpful in being able to operate in the future, but it doesn't mean that's the only way to accomplish the latency, throughput, integrity, and availability that you need to complete the desired function. It just may be one mechanism for doing that. For example, a solution, a technology that enables managed spectrum coupled with precedence and preemption might be sufficient to get your required performance. And so these are the kind of things that the community, I think, needs to explore. And this is where the collaboration between NASA and the Open Generation Consortium provides us a joint opportunity to explore these issues together. I'm going to pause here because this is really theoretical, but I just wanted to make it clear that we're not necessarily locked in that 5G is the solution, but we see 5G showing significant promise, and we need to explore that promise. Okay. And I think I said all that. So let's look a little bit at the issue of automation. So I'm going to talk about kind of a spectrum, or sometimes people refer to levels of automation. And in automated driving, there's a very popular levels of automation adopted by the Society of Automotive Engineers that many of you probably are familiar with because it's used quite extensively in the popular press, as well as in regulations in the ground vehicle community. And one of the things that it's important to focus on, especially in aviation, is functionality that's being automated. So this is one potential scale of levels of automation, and I'm using it here not to say it is the scale and the only scale that should be used, but I'm using the scale here to make some additional points on the next slide. And the notion here is that there's different functionality that is being automated in these different 5 levels. On the left, you have very low-level kind of in-a-loop decisions regarding flight stability of the aircraft, where the pilot is in continuous control, but you might have the pilot connected to the flight control surfaces with automation, like a fly-by-wire system that actually might put some limits on the pilot's authority, aiding them in ensuring flight stability. The next level, flight path guidance, the pilot might be in the position of setting a heading and altitude and speed, and the aircraft automation will make all the decisions about what thrust the engine should have, the deflection of the flight control surfaces, to enable that flight path to be realized. And it's really just a heading and an altitude. Flight path management would be a series of waypoints that you say, I want this aircraft to fly this waypoint, then this waypoint, then this waypoint, and this waypoint, and the automation figures out how to accomplish that in terms of the headings and altitudes that would be required. So you could think of flight path guidance as an autopilot and flight path management as a flight management system if you were thinking of a commercial airliner. And then a flight path selection would be where you figure out what that flight path should be based on environmental conditions, winds, what is the right flight path, as well as airspace restrictions, etc. What is the right flight path to operate on? And one might think of this as a flight planning system that exists in the airlines today. And then the other is the notion of operational control, where the decision even to fly or not to fly, and some very high level decisions are made that requires reasoning and judgment. And on the left, we have very well-defined structured decisions, and all the way on the right, we have very complex unstructured decisions. And we are exploring automation for all of these levels as an aviation community. We are have very high confidence on some of the more physics-based, well-defined structured decisions that are on the left. But some of the aircraft that are being planned for the future are going to be automating many more of the functionality, moving more towards the right. And so this was a theoretical, and then I'm going to use this as an example as it relates to communication on the next slide. So any questions on this or comments? Okay.
One question here. This is
Sure.
Prashant Anand from Bell Labs. Here, where would you put things like collision avoidance between aircraft?
It would probably be on the flight path selection. So you want to avoid a hazard, and flight path selection is all about avoiding hazards, and changing the flight path to avoid that hazard would be, it's a higher order, increasingly unstructured, very complex decision to do things like collision avoidance. Is that helpful?
Yep, thank you.
Yeah, it's more toward the right side of this chart. Any thoughts, other questions?
Oh, it's Rick. I just, your description of operational control, I can actually imagine an automated system that dispatches human pilots. So you could have operational control done by automation, but then the flying done by humans, you know, so there are weird combinations that you could do.
We have that today, Rick.
Yeah.
It's called Uber and Lyft.
Exactly. There you go.
So you invented something really cool just about 10 years too late, but well done. But yeah, Rick is absolutely right. You could have automations at any of these levels, and some of the lower levels be done manually. What does this mean for communications? So this is a notional or conceptual diagram. So this is not based on any data. This is just to make a point. A lot of people feel that as you move your level of automation to increasingly automated system, your need for communications goes down. Well, your need for communications for the functionality of controlling the aircraft may go down, but your need for communications for situational awareness, you might, as you go to higher order decisions being made, let's say on board the aircraft, you're going to need more data to be communicated to the aircraft so that the situational awareness is available to the automation on board the aircraft to make these decisions. So it may have different parameters for the communications performance, but theoretically, your demand for communications doesn't disappear as you become more and more automated. It just changes the required performance of that communications. And operational control, by its very nature, the operator is the entity that's causing the flight to be operated. Think airline as an analogy to air transportation, and that level of communications probably remains constant as you move along these, because if you're a pilot on board the aircraft and the aircraft is doing, the automation on board the aircraft is doing flight stability, the information you're getting from the dispatcher doesn't change at all. If you're then using a flight path management or an FMS on board the aircraft to manage the flight, your workload may change and your role on board the aircraft may change, but the amount of communications you need from the dispatch center would not change substantially. So this is theoretical, and this is really to help at least me make the point for myself that the need for communications doesn't disappear as we go to increasingly automated operations, and that in fact it may change the required performance of that communications, but it doesn't disappear. Thoughts on this?
Yes, I will have just first, I really like this curve, Andy, and I think that it makes very well the point that the nature of what you are communicating is what changes depending on the level of automation. And so looking at the right side, I could imagine, I wanted to see what are your thoughts on that. Examples of what type of communications we are talking about on the right side. It could be, for instance, the drone receiving surveillance data that's captured on the ground, and now it has to be transmitted. The aggregate has to be transmitted, and so the drone has access to all the situational awareness. That's one example. Thinking of what other examples you would like to mention.
Well, for example, weather. Information about weather. Someone else, and I can't remember who, brought up about collision avoidance. If your collision avoidance algorithms include information from sensors that are not on board your aircraft, whether it be information from other aircraft that are transmitting to you about their location, or information from the ground about the traffic situation awareness, that situational awareness data has to get to the automation on board the aircraft for that automation on board the aircraft to function correctly.
Yes, exactly.
And weather and traffic are the two best examples in my mind.
This is Prashant Anand once again from Nokia. Here, when you say automation, you're particularly referring to automation on board the aircraft only. Couldn't that automation also be via connectivity from the cloud, and the automation is actually in the cloud, and then this changes?
Yeah, absolutely. But then if the automation is in the cloud, the dependency on comm goes up because you're sending more aircraft control type commands to the aircraft. So using the example of collision avoidance, if the automation for collision avoidance is on the ground, I have to send the new flight path guidance pretty urgently up to the aircraft with, I have to have high availability, low latency, and I have to have assured delivery that my message is going to get to that aircraft, because if I'm trying to avoid a collision, I got to send that information right away. What it really I'm sending is flight path guidance. I'm changing the heading of the aircraft to avoid that collision. So it would be the COM would increase. So this is a conceptual diagram if the automation is on board the aircraft, but the more automation you put on the ground, the more you move to the left of or the higher you get in the performance of COM in the need to operate safely. Did I make sense, or did I?
Yeah, that helps. Thank you.
Okay, so with that, I'm going to kind of shift gears and talk a little bit about a couple of opportunities for collaboration, because that, as Layla was pointing out, that really is what we want to talk about today, and that's why there's 5 of us here to talk about those different collaborative opportunities. So I'm really going to talk about 2 specific activities that we have going on at Langley that we think present the greatest opportunity for collaboration. Langley, we have to be funded to, we have to have funded research that we could align to a collaborative effort. And so we have, existing funded activities that we could align to a potential collaboration with the Open Generation Consortium. So I'm going to talk about the first one. We call it CERTAIN. It stands for City Environmental Range Testing for Autonomous Integrated Navigation. And there's one thing I've learned. I haven't been at NASA very long, but I've worked with NASA for much of my career. And there's one thing I learned is NASA is brilliant when it comes to engineering and science, but they're also brilliant when it comes to coming up with acronyms. And this one's a mouthful. But CERTAIN is what amounts to a testing range, a capability to do flight operational testing at the Langley Research Center. So if you look at the picture on the left, the satellite imagery there shows Langley in red, nestled up next to the Langley Air Force Base. So the red is the NASA Langley Research Center, and the blue is the Langley Air Force Base. And we share access to the runways at the airfield, and the Air Force operates the airspace, the Class D airspace, and the tower at the Air Force Base. On the right, you see different pieces of Langley's, area, the center, that's broken up into different blocks of airspace that make up the CERTAIN range. And that's an area where we can do operational flight testing, as well as use unmanned aircraft for center missions, to actually use them for activities at the center itself, and not just use them to research aeronautics, but use them for the functioning and providing services to Langley itself, the Langley Research Center. And I'm going to give you an example in a second. So again, we have a multi-year plan for the CERTAIN range, where we're really somewhere around achieving goal 1 and 2 at this point. But we have longer-term plans, and this is something that will enable us to explore not only unmanned aircraft and small UAS, but also look at urban air mobility and advanced air mobility as a whole. So one of the things we've done at the CERTAIN range is we've created the capability to operate small unmanned aircraft for perimeter security. We have an Office of Protected Services, think of that as our security, that are responsible for monitoring the fence line. And we have come up with a capability to use small unmanned aircraft to do that fence line monitoring. And so we're at the point where we've done a proof of concept demo. We're not quite at the point where we're operating on a daily basis, but that's one of the things we hope to eventually pivot to, where we're operating routinely to do perimeter security. And one of the things that we would need, of course, is high reliable communications, not only for flight operational control, but because we're using surveillance cameras, we need to have broadband communication back to our operations center, back to the Office of Protected Services, so they can do the monitoring. And this has been achieved, and our flights occurred within the past couple of months, and we continue to work toward this. And I don't know, Jennifer, you were leading a lot of this effort. Do you have anything you want to add?
Good afternoon. I'll just quickly pop on and say about two quick things. The first being in terms of the movement of data, that the movement of high bandwidth, low latency data would be very, very attractive in conjunction with this use case. And then the other thing I'll quickly mention in terms of, Andy pointed out very clearly, and it says at the top of the slide, this was a proof of concept demonstration to really give NASA Langley Research Center an opportunity to see how small UAS could be incorporated into the center operations work, again, as Andy mentioned. In terms of a production type operation for perimeter surveillance, we would think more in terms of not necessarily utilizing a large vehicle such as the Alta 8, which is shown in the slide in the upper right corner, but something more akin to a smaller drone in the box type of solution that would deploy autonomously, do its circuit, dock. Also, with respect, I'll say three things then, Andy, you shouldn't have gotten me going. In addition to the movement of the video, we also, of course, don't anticipate a human sitting and monitoring live video looking for an anomaly. We'd also like to have some artificial intelligence, machine learning embedded into this operation as well. And in terms of a data fabric component that we're also going after at Langley, creating that very rich environment of data where, again, the movement of high bandwidth, low latency data is critical. Well, I'm here if you need me, and I'll go off camera now for a while.
But there's also the potential to link the two, to use the artificial intelligence to cue the flight operations where to focus data collection efforts. So,
well said. Thank you.
And so that, again, that's what we're continuing to explore.
And just a question there. So you're using LTE, it says on the bullet point there, or is that to be done, or are you doing that now? And then do you have plans for 5G? Okay.
The next slide, oops, winding in advance. There we go. Shows the actual data flows themselves. So we are using LTE for flight control, and I believe we're using a different radio link for the actual data streaming. But ultimately, it goes into our intranet and to our Mosaic. Again, we're masters of the acronym. Mosaic is essentially our control center of where the information is available. I don't know if, Jennifer, you have anything you want to add?
I'll just point out that, as you stated, and we utilized the 4G LTE cell network for this initial proof of concept, and then we did use VHF for the voice comm at this point.
And then the other thing that we have the capability, that we haven't done this yet, we have the ability to also do simulations, and we can connect actual flight operations to a simulated environment where we could do live virtual constructive simulation. Ken, you have a question? Oh, okay. Just a hot mic. I think that's all I want to say. And we are, right now we do use visual observers for the BV loss operations, but I'm going to get into a little bit more detail on how we're doing BV loss in the future.
Hey, Andy, this is Ajit Kahadu. I have a question. On the certain range, I noticed you're next to the water. Are flights over water part of the NASA area, or are you limited just to the landmass?
You're a great straight man. That's where we want to go next.
Glad I set you up.
Thank you, sir. So let me talk about one other project, and then we'll talk about where we might go next. We're looking at urban air mobility, kind of under the advanced air mobility umbrella, which includes operations at what we're calling high-density vertiplexes, or vertiports, where there's a lot of operations around the vertiport. And there's a lot of research questions associated with that, and we have several different components to our research. But one of the things we have to do in order to further that research is we need to be able to operate small UAS or UAS beyond visual line of sight. So under this project, we are in the process of creating a cascading or building upon capability to operate beyond visual line of sight. So we are working toward eventually being able to operate a quite far distance beyond visual line of sight. But right now we're looking at low risk, kind of expanded visual line of sight, and then moving toward that's where we're operating today, but we want to be able to operate true BV loss. And we have our COA is in process right now, and it's enabled by surveillance. And so we have a number of different surveillance capabilities that are in place, and we have additional surveillance that's planned. And we also use the ONRA Smart Skies capability to integrate all of these different surveillance sources. So the large circle, and I can't tell you what color that circle is because I'm colorblind, but the large circle is an L-star radar, which is at Langley. We also have two GA 9120s, which are mounted on a gantry structure at Langley as well, which is kind of on the north side of Langley, and we have them looking off to the east. In collaboration with Hampton University, we have a radar, a Skylar radar, that is also looking to the east, and all of these different surveillance sources can be integrated together and fused into a common traffic display using the ONRA Smart Skies capability. So this is stuff that we have in place or soon to be totally in place, offering surveillance. And as you can see, it includes a significant amount of a maritime area, and that's on purpose because we see that as an area of good research potential to explore not only urban air mobility operations, but other unmanned aircraft operations as well. I don't know if you, Jennifer or Sam, you have anything you want to add?
Andy, it's Rick. Question. The FAA has defined the use of visual observers as beyond line of sight of the actual pilot as BV loss. So would this be BV loss without the need for visual observers to see the aircraft at all times?
Yeah, no asterisk. No, it's without visual observers is the goal.
Great, thanks.
Jennifer, Andy, Sam, Tommy, and Danette, thank you so much for joining us today for this roundtable. It's been a fascinating discussion, so we really appreciate it. And I also want to highlight our next Government Liaison Roundtable, so please join us next month on April 21st. We'll be featuring Art Heinemann of FAA's UAS Integration Office to hear the UAS safety perspective at that meeting. So we look forward to that in just under a month. So thank you again for joining, and we're going to sign off now and have a great day.